Okay, so Isaac Newton's three laws are very important to us in Year 12 physics, so it's important that you know what they are and what they mean. So Newton's first law was that an object will stay at rest or in constant motion unless acted on by an unbalanced force. So this is often paraphrased as inertia, which means an object's resistance to change in its motion. So it means that you need to apply a force to make something move, to apply an unbalanced force to get it to move, and you also need to apply an unbalanced force to change its velocity, change its motion. What this means in practice is, one of the important applications is that when you see things described as having constant velocity means acceleration equals zero. And if acceleration equals zero, then the net force equals zero. And if there is no unbalanced force, then an object will remain in constant velocity. So constant velocity or constant speed means that there's no unbalanced force acting on it. We'll see what that means. Second law, where the familiar F equals ma, being careful to notice that it is the net force, the sum of all the forces, that is equal to ma. Another way to think about that is A equals net force on m. So the acceleration is proportional to the net force and inversely proportional to the mass. So if you have a larger mass, you'll have a smaller acceleration. A smaller mass gives us larger acceleration. So those two quantities are inversely proportional, and obviously these are directly proportional, that a larger force will give a larger acceleration. Net force, of course, means all the forces are added together. So if we have a free body diagram here, here's the centre of mass of an object. If the net force were to equal zero, all the forces would have an equal and opposite partner, and they're all balanced there. So their net force equals zero. Newton's third law is a little tricky. We're going to talk about this a little bit. When one body exerts a force on another body, the second body exerts an equal and opposite force on the first body. So this is the equal and opposite reaction. So important notes here, you get action and reaction forces, and they apply to different objects. They apply to the first body and the second body. These forces are equal in magnitude and opposite in direction. So let's have a look at one of these. So here is a ball hitting a cricket bat, bat hitting a cricket ball, the same thing. So we have the force of the ball on the bat. So that's the force that the ball applies to the bat. So that will be that way. It would be better to draw it that. So it is clearly the force on the bat. There is also the equal and opposite force, the force of the bat on the ball. And I want you to get into the habit of thinking about forces in this way. Force of something on something. So the force of the bat on the ball will be like that. So the size of these arrows should be the same. We'll just pretend that they're the same in magnitude and opposite in direction. And you can see it, they're very clearly acting on two different objects there. So there's a force acting on the ball and a force acting on the bat. Why is it that we see, if these sort of forces are identical, why is it that we see the ball moving away and the bat normally not being affected by hitting the ball? It's because the bat is normally attached to a person, and that person-bat combination normally has a lot more mass than the ball. And so for the same force, if you have a small mass, you're going to have a large acceleration. Likewise, if you have a large mass, you'll have a relatively small acceleration. So the forces that they exert on each other are identical, but their accelerations will obviously be very different. So another example, here's an apple hanging from a very poorly drawn tree. If I were to ask you to draw the forces acting on the apple, I think you would all straight away draw the weight force, which we can describe as the force of the earth pulling on the apple. Which we often label as mg, the weight force. And if you're asked to draw the reaction pair, the action-reaction pair, so the opposite reaction to that force, a lot of you may draw some sort of force around the twig here, some sort of tension force here. But if you think about it, the reaction to this force is the force of the apple on the earth. So there is a force of attraction here between the earth and the apple. You'll see later on when we study Newton's law of gravitation that any two objects attract each other equally through gravity. So there is an equally strong gravitational attraction of the earth pulling the apple down as there is the apple pulling the earth up. So why, when this branch breaks, do we see the apple fall towards the earth and not the other way around? Well, it's just like we mentioned before. For the same force, you can either have an object with a very large mass having a very small acceleration, or you can have an object with a very small mass having a very large acceleration. So in this case, this here would be the earth, this here would be the apple. So in theory, the earth will move very slightly when that apple falls, but in reality it'll be much, much, much too small to ever be measured. So those are action-reaction pairs.